we've had a look at a titration curve. This is what happens if you get a strong acid like HCl. So you've got HCl in there, and you run sodium hydroxide into it. You get this curve here. So here's the pH, and here's the volume of NaOH added. And this here is the equivalence point. Okay, that's when you've got, for every 1 mole of acid, you've added 1 mole of the NaOH and neutralized it. Okay, so we're familiar with that. We know how to calculate all the different points of that curve. Let's see what happens now if we replace that strong acid. Instead, let's have a weak acid in there. Let's have ethanoic acid. I'll just call it HA. That's ethanoic acid. What would the curve look like? Well, it looks something like this. Obviously, it's going to start off at a higher position, and it looks something like that. Okay, just went a bit funny there at the end, but okay. So I'm going to rub out the strong acid now. Let's get rid of that. We'll have a little think about what's happening with this weak acid. So one of the things to notice here is that the equivalence point is actually slightly alkaline. Okay, so it's sort of the middle of that vertical bit. The equivalence point is above pH 7, and there's a reason for that, which you can have a think about in a bit. But right, let's see what's going on here then. So right, what we've got is we've got our ethanoic acid, HA, and we're adding OH minus, and we're turning it into A minus and H2O. Right, so at this point, at the start point here, right down here, we've got 100% HA, and yet we'll have a tiny bit of A minus, but like virtually we'll just call that 0% A minus. And at the equivalence point, it's the other way around. We've now got, we've got 0% HA, that's all being reacted, and we've got 100% of the weak acid being its conjugate base. Okay, so at this point here, which is half the equivalence point, so that was, we've added 25 centimeters cubed for the equivalence point. This is where we've added 12.5. You'll be able to see that we have a 50% of HA there and 50% of A minus. This is called a half equivalence point, and this is pretty important. There's a half equivalence point. Right, so let's try and have a think about what's going on here then. Okay, now when we're working out buffer solutions, we always rearrange our Ka expression to be like this. So we put H plus is equal to Ka multiplied by the concentration of HA over A minus. Okay, so now at the half equivalence point, what can we say about the concentration of HA is equal to the concentration of A minus? Okay, we've got 50% of each one. So that means this fraction here, that is equal to 1 at the half equivalence point. So at the half equivalence point, then we can say that H plus is going to be equal to Ka. Now we're going to take minus log, so take minus log of both sides of the equation. And what do we get? Well, the minus log of H plus is equal to pH. And the minus log of the Ka is given a special name, and we call that pKa. So if we go back to our graph, and if we draw what we can say here is dot a line up there from 50% and dot a line across to this axis, and that value there on the pH axis is equal to the pKa of the weak acid. So that means you can find out the pKa of a weak acid by doing this experiment, and this is one of the required practicals. So you have your burette of sodium hydroxide, and you have your flask of weak acid there, and you put a pH meter in there, and you add the sodium hydroxide bit by bit, and you plot this curve. Once you plotted the curve, then you find out where the equivalence point is, and you can see where the equivalence point is because it's where that vertical line is there, where the curve goes vertical. You find out the half equivalence point by taking that, halfway along this axis. Then you can construct that purple line, and that will give you the pKa of the acid. Okay, so you've got the pKa of the acid. How do you find out the Ka from the pKa? Well, we know that Ka is going to be equal to, just like the pH expression, Ka is equal to 10 to the power of minus pKa. And so you find Ka there. So that's how you can find that. Right, there's another important point here on this curve is let's have a little think about, let's get rid of some of this stuff here. Right, so we can see here in this region of the graph, we've got fairly decent amounts of HA. We've got lots of HA, and we've got lots of A minus. So that means means it is a buffer solution. So when you've kind of half neutralized a weak acid, you've essentially got a buffer solution there. And let's just see what's happening. So we add a little bit of NaOH. Look at that purple arrow there. You add a bit of NaOH. What happens is the pH starts sneaking up a little bit. It goes up a bit, but it doesn't go up loads, does it? The solution's buffering, and it will carry on just sneaking up a little bit until you get to about here, and then you're going to add one drop of alkali, and it will shoot up. And at that point, it's stopped being a good buffer solution. Okay, and why has it stopped being a good buffer solution? Well, it's because you've got there's not much HA left. All the HA has been exhausted, and it's not a good buffer anymore. Okay, let's think about the opposite direction. So if you remove NaOH from this, and of course you can't physically remove NaOH, you can't take the OH minus out, but if you could, the pH would just drop a little bit. You can't remove OH minus, but what you can do is you can add H plus. It's the same as removing OH minus, and you can see the pH doesn't actually change very much when you add H much. It just sneaks down a little bit. Of course, when you get to there and then you add a few drops of HCl, then it would drop right down, and it would stop being a buffer. And the reason why it stopped being a buffer there is because you haven't got any A minus left over. That's run out there. So the titration curve for a weak acid against sodium hydroxide shows a lot of things. It enables us to work out the Ka of the acid, and it also gives us some insight in this region here is what's happening in a buffer solution. Don't forget the half equivalence point. That's really important. And just as half equivalence point, pH is equal to pKa. And that is because HA concentration is equal to A minus concentration. So the value of that fraction, HA over A minus, becomes 1. And then, we're very familiar with this rearrangement of the Ka whenever we do a buffer calculation.